So good morning, everyone. I'll be talking about some dynamics of the standing meanders in the Antarctic circumpolar current, and as well as their response to wind today. So as the Antarctic circumpolar current continuously flowing around the Antarctic continent, wind input momentum at surface, topography remove momentum at bottom. But one of the major features of this current attracting lots of research interest is the transport of the ACC is not sensitive to wind increase at surface, even though wind is a momentum source for this current. And standing meanders are found to be important for the dynamics of the ACC. So this study is really about looking at the role of the standing meanders in the ACC's insensitivity to wind. So here I have some examples for the standing meanders in the ACC marked by the red boxes here in this map. And the formation of the standing meander is really related to the mean flow capture Rossby wave, which have same phase speed with the current speed. Many previous studies have suggested the dynamical importance of the standing meander, like Evans and Chizzy 2014, they found the standing meander will facilitate meridional heat transfer by increasing the local buoyancy gradient. So in their eddy heat flux divergence map, we can see the enhanced eddy activities are really concentrated in the standing meander regions. Some other studies like Dufour et al. 2012, they found the standing meander will dominate the response of the overturning circulation as well as the ACC to the wind. And in our study, we will take this Macquarie meander, for example, to look at the problem. And the Macquarie meander is located in south of Tasmania and New Zealand. So as I just said, we are particularly interested in what role played by the standing meander in the ACC's adjustment to wind. There is actually already an existing framework about this proposed by Thompson and Vigabato 2014 or TNG14. So in their framework, they suggested if wind increase at surface, it will steepen isopignal upstream of the standing meander. That will lead to a stronger mean flow by increasing the flow bioclinicity. And this stronger mean flow will capture a different Rossby wave, forming a standing meander with a larger curvature. As this meander flexes, the eddy momentum flux is found to be stronger, thereby transferring more momentum downwards, leaving the ACC not sensitive to the wind increase at surface. So this is a great framework, but has not been fully validated, especially the first step here, the increase of bioclinicity of the mean flow. They also explore the vertice balance of the standing meander because it is related to the curvature of the, it is related to the curvature of the standing meander, the second step here. But the underlying mechanism of the vertice balance is still not very clear. The vertice balance diagnosed in their study was its quasi-geostrophic vertice balance here. From left to right is advection of relative verticity, stretching, and advection of planetary verticity. I'll just call them advection, stretching, and between for short. So they firstly plotted the vertice balance maps at around 250 meter depths. And what they found is the vertice balance is dominated by advection and the stretching, where beta V is one order smaller than the other two. And beta V has a smoother pattern than the leading order vertice terms. Interestingly, although the formation of the standing meander is related to the generation of Rossby wave, the vertice balance is inertial, like dominated by advection of relative verticity. But it wasn't explained why the vertice balance behaved like this. And in our study, we use a regional model simulating the Macquarie meander region, the red box we saw earlier. We would like to diagnose the vertice balance of this standing meander and at the same time understanding more about the underlying mechanism of the vertice balance for this meander. The model we use here is MITGCM with 1/20th degree horizontal revolution. So we can see lots of some mesoscale motions from the animation of the surface temperature here. It is driven by wind forcing at surface. That's a repeater forcing from excess OM to O1. And it's configured with high resolution bathymetry, so we can see lots of small-scale abyssal hills as well as a large Macquarie Ridge in this model. So using this model, we reproduce the results in TNG14 in terms of the vertical balance is between advection and stretching, where beta weight is 1 order smaller than the leading order terms. But at the same time, we also notice the vertical structure of the vertical balance. So the left plot here are vertical sections of vertical balance near the mid-latitude of our domain. The black box marked the location of the Macquarie meander in our domain. And we can clearly see there are vertical structure especially in advection and stretching, like large scale patches are found at surface, and bottom patches have much smaller horizontal scale and they decay very quickly from bottom up. In contrast, beta weight has a relatively uniform structure throughout the vertical column. So we would like to know why vertical balance look like this and why they have this vertical structure. So to understand that, we further developed a quasi-geostrophic theoretical model. That's a simple 2D model trying to simplify this question a bit. The governing equation just starts with the evolution of QGPV, and QGPV is related to the absolute verticity and stratification. Oops. We apply some assumptions to this model, including linearization. We also assume a zonal background velocity and a steady state. We further simplify the computation by making the bottom topography one-dimensional and has this cosine shape, and K is a wave number of our bottom topography. We also assume stratification doesn't vary with depths. And the boundary condition is just vertical velocity is 0 at surface and follows topography at bottom. Finally, we inserted a waveform solution, and the governing equation just become an ODE for phi, and phi is the vertical structure of the perturbation. All of this just to describe a 2D perturbation over a 1D bottom topography. And the governing equation can be further simplified if we make lambda square equal to this. Lambda square is a very important parameter here. As you can tell, lambda is the eigenvalue of this ODE. So depending on the sign of lambda square, we will have different formulas of analytical solution which are associated with 2 regimes in the QG model, decaying or radiating. And we will see this very soon. And what determines the sign of lambda square? And we can easily tell from this formula here. It is related to the background velocity as well as the horizontal scale of the topography. And K is a wave number we saw from the last slide. And now we can have a look at the implications from the analytical solution. So if lambda square is smaller than 0, that means we have a small scale topography or large background velocity. This will give us a decaying analytical solution. In contrast, if lambda square larger than 0, that means we have a large scale topography or small background velocity, that the analytical solution doesn't decay. It's actually in a cosine and sine shape. It's a radiating solution. And these 2 regimes are associated with 2 types of vertical balance. For the decaying regime, stretching is balanced by advection of relative verticity. That's the verticity we saw in TNG14 and in our original model. For the radiating regime, stretching is balanced by beta weight. That's where a Rossby wave becomes important. And the shift between these 2 vertical balance is partly due to stretching and advection. They are scaled by the background velocity, while beta weight is not. If we write down the analytical solution for the quasi-geostrophic verticity terms, the left box here, we can clearly see advection and stretching, both of them have background velocity in their expression, while beta weight is not. And we will see this feature later. And now we can plot the solution out and see the difference between the 2 regimes. We've already know there are 2 ways of changing the sign of lambda square, like changing the regime of the QG model. One is by changing background velocity, and the other is altering the horizontal scale of bottom topography. We firstly keep the background velocity the same and look at different horizontal scale of bottom topography. So for small scale topography, I use 30 kilometer here. So K is large, leading to a negative lambda square. For large scale topography, I use 500 kilometer here, which gave us a positive lambda square. The upper panel plotted the vertical sections of vertices terms showing their horizontal distribution. The rest of the vertices terms in each case have exactly the same distribution, so they are not all plotted here. So the small scale topography gave us this small decaying feature, decays very quickly from bottom up. In contrast, the large scale topography produces large and relatively uniform patch of vertices terms. And the bottom panel shows the vertical structure of vertices balance. For the decaying regime, stretching is balanced by advection of relative verticity, and both of them just decay very quickly from bottom. This is generated from the bottom flow going up and down the small scale topography. It doesn't generate Rossby wave, but only dissipate away from the topography. For the radiating regime, stretching is balanced by beta wave. That's when the Rossby wave is generated and come into play. So stretching here is balanced by beta wave, and all of them have relatively uniform structure compared to the quickly decaying manner in the decaying regime. And now we keep the topography scale the same and look at shared background flow, which allow us to have two regimes in one water column by changing the background velocity. So the left plot here is the velocity share we use here, and the right plot is when we insert this background velocity to our QG model, and we will get this result of vertices balance. The regime change happens around 1.5 kilometer. Lambda square becomes from positive to negative because subsurface velocity is larger. Correspondingly, at the bottom, stretching is balanced by beta wave, but as we go upwards, advection and stretching, they become more dominating. This is exactly because advection and stretching, they are scaled by the background velocity, while beta wave is not. So beta wave is relatively uniform throughout the river column. So although this QG model is simple and has lots of assumptions, it reproduces most of the features we saw in the original model with relatively realistic configurations. Like the large scale patches we saw at surface is initiated from the large scale topography and amplified by the shared background flow. And the bottom decaying features is from the interaction between the bottom flow and the small scale topography. And since we only look at one wave number for topography every time in the QG theory, but this realistic bathymetry has a whole range of different wave numbers, is more complicated. The features of vertices balance in regional model can be taken as a superposition of different cases in the QG theory. And what we learned about the mechanism of from the QG model is that it is the bottom flow interacting with large scale topography that generates the radiating Rossby wave that captured by the mean flow to form the standing meander. And the background shear there is there to amplify the signal generated from the bottom. And it especially amplifies stretching and advection, leading to the vertices balance we saw in TNG14 and in our original model at subsurface. And our results highlights the importance of the bottom flow. And theoretically, if the bottom flow changes, it could also lead to the standing meander flex differently because it is the bottom flow that interact with the large scale topography to generate Rossby wave we need to produce a standing meander. And this is true in our regional model. Now we use this regional model to explore a bit about wind sensitivity. The solid blue line in the left plot here is the time series of the transport at western boundary. That's the strength of the inflow. to our regional model, and it varies in phase with the wind stress in this region. And you can also consider it as a time series of wind, if you like. The total transport is further decomposed into barotropic and the barocolinic part. We multiplied the bottom flow with the ocean depths as our barotropic part, and what left is a barocolinic component. So we can see from this plot that although barotropic part contribute much less than the barocolinic to the total, it dominates the variability of the total transport. And over the year, barocolinic changes only around 10%, while the barotropic part changes as much as 100%. We then selected weak or strong current months depending on the strength of the total transport at western boundary, which is also the barocolinic transport of the inflow. And we then averaged several diagnostics in these 2 months every year. The red plot here is the sea surface height contours corresponding to the weak and strong current months. And indeed, in agreement with this QG theory, the standing meander curved more significantly in response to the stronger barotropic flow. And here I also show the vertical sections of advection of relative vorticity for weak and strong current months. And overall, they generally have the same structure, but at some places like here and here, the increase can be a factor of 2. This is consistent with the magnitude of the increase in the barocolinic transport over the year. So based on these results, we would like to extend the framework in TNG14. Like in addition to the increase of barocolicity, barotropic part can also contribute to the ACC's response to wind. Actually, in our model, when wind increase at surface, it is the barotropic part of the flow increase in response to the stronger wind. And the stronger barotropic flow interact with large-scale bottom topography, generate a new Rossby wave with larger wave amplitude. And this radiating Rossby wave generated at bottom will propagate upwards and get amplified by the background velocity shear. Finally, it will form a new standing meander with a larger curvature in response to the enhanced wind at surface. So this is more like a bottom-up mechanism in which not only the Rossby wave is generated, but the entire vertical structure of the standing meander is maintained by the bottom flow interacting with bottom topography. So to summarize, what we learned from the QG model about the mechanism is the meander formation is controlled by the mean flow. Like the barotropic part is there to interact with the large-scale topography to generate a radiating Rossby wave. And the barocolinic part is there to amplify what is generated at the bottom, leading to the dominance of the vorticity balance between advection and stretching. That's what we saw at subsurface in the numerical models. And finally, in terms of the wind sensitivity, the ACC meander are sensitive to the changes of the barotropic flow, implying a faster time response to the increase in wind. And I think I'll leave it here and happy to take any questions. Thank you.